Consider this. You flip a switch and a light comes on. That happens because electricity flows through a metal wire, usually copper. Metals are all around us. We see them in buildings, we see them in cars, we see them in the coins in our pockets. But what makes a metal, well, a metal? What gives it the incredible ability to carry an electric current so easily? The secret lies deep inside, at the level of atoms and electrons. It's a fascinating world, and we can start to understand it with a simple picture. Imagine a metal as a big, orderly jungle gym of atoms. These are the metal ions. They are positively charged. They are locked into a neat, repeating pattern called a crystal lattice. Now picture tiny particles zipping all around this jungle gym. These are the electrons. In a metal, some of the electrons are not stuck to any single atom. They are free to roam throughout the entire structure. Scientists call these free electrons. They form a kind of sea of negative charge, flowing around the fixed positive ions. This sea of electrons is the key to everything. This simple idea, called the classical free electron model, is incredibly useful. It helps us build a mental model for what happens when you connect a wire to a battery. The battery provides a push, an electric field. That gets all those free electrons moving in the same general direction. This organized flow of electrons is what we call an electric current. It's like a gentle river flowing through the atomic landscape of the metal. Understanding this model is the first step toward figuring out why some materials are great conductors and others aren't. This model, first dreamed up by a scientist named Paul Drude over a century ago, gives us a starting point. It's not perfect, as we will see, but it's a brilliant first guess. It provides the basic vocabulary for talking about electrical conduction. It introduces ideas like collisions, resistance, how temperature changes things. By starting with this simple picture of a sea of electrons, we can build our understanding of a deep and important property of the matter that makes up so much of our technological world. It's science, and it's all about looking closely at the world and trying to figure out the rules. So, we have our sea of electrons. But how do we turn that picture into a real theory? We need to set some ground rules, or assumptions. First, let's assume the electrons are like a gas of tiny independent particles. They zip around freely and don't really notice each other. Think of them as billiard balls that only change direction when they hit something much bigger. Second, we assume the positive ions, the jungle gym structure, are fixed in place and don't move. They just act as stationary obstacles for the electrons to bump into. A third key assumption is about collisions. When an electron hits an ion, the collision is totally random. The electron basically stops and then shoots off in a new, unpredictable direction. It's like a pinball hitting a bumper. The time an electron travels between these collisions isn't always the same, but we can talk about the relaxation time. A shorter relaxation time means more frequent collisions. Finally, this whole model uses the rules of classical physics, the kind of physics that describes everyday objects like baseballs, not the weird rules of the quantum world. So with these rules, we can describe what happens when we apply an electric field. The field gives every free electron a little push. Without any obstacles, the electrons would just go faster and faster. But they keep bumping into the ions. Each collision resets their motion. The result is that the electrons don't accelerate forever. Instead, they gain a tiny average forward motion on top of all their random zipping around. This average forward speed is called the drift velocity. The electric current we measure is just the total effect of billions and billions of electrons drifting together. A shorter relaxation time, more frequent bumps, leads directly to higher resistivity. This simple connection between collisions and resistance is a huge success of the model. Now, what causes these electron-slowing collisions? It turns out there are two main culprits. The first is imperfections in the metal's crystal structure. Imagine our perfect jungle gym having a few posts out of place, or having a different kind of post stuck in it. These are like impurities or defects in the metal. They are always there, and they cause electrons to scatter. This part of the resistance doesn't really change with temperature. It's a fixed property of that specific piece of metal. It's like having permanent obstacles in your running path. The second cause of collisions is heat. The ions in the metal aren't truly fixed. They are always vibrating a little bit. As you heat the metal up, these vibrations become bigger and more energetic. Think of the posts in the jungle gym shaking back and forth. For a tiny electron trying to zip past, a vibrating ion is a much bigger and harder target to avoid. More vibrations mean more collisions, and therefore, more resistance. This is why the resistance of most metals goes up as they get hotter. the hallway gets more crowded and the people start dancing around. This leads to a beautifully simple idea known as Matheissen's rule. It states that you can find the total resistivity of a metal by just adding up the resistivity from each source. So, the total resistivity is the part from the fixed impurities, plus the part from the temperature-dependent vibrations. It's like saying your total travel time is the time spent at permanent red lights, plus the time spent in traffic jams that get worse during rush hour. This rule is incredibly handy for engineers and scientists. Why is this so useful? Imagine you want to know how pure a sample of copper is. You can measure its resistance at a very, very low temperature. At temperatures near absolute zero, the lattice vibrations almost completely stop. The traffic jam part of the resistance goes away. Any resistance that's left must be due to the permanent red lights, the impurities. So, by cooling the metal down, Matheissen's rule lets us separate the two effects and get a direct measure of the material's purity. It's a clever trick that works surprisingly well in many situations. For all its simplicity, the classical free electron model gets a lot of things right, especially for common metals at everyday temperatures. Its greatest success is explaining the basic fact that metals conduct electricity at all. The idea of a sea of mobile charges that can be pushed by an electric field. It immediately separates metals from materials like glass plastic. Electrons in those materials are tightly bound and cannot move to form a current. This fundamental insight is the bedrock of our understanding. Heating a metal makes its ions vibrate more, causing more electron collisions and higher resistance. We see this in the real world every day. A copper wire gets slightly more resistive when it warms up. This matters for power lines, and for the filament in an old-fashioned incandescent bulb. The filament glows because its high resistance makes it extremely hot. Finally, the model gives a qualitative feel for why different metals conduct differently. More free electrons per atom. Longer time between collisions for electrons both make a metal a better conductor. The model's numbers are often in the right ballpark, maybe off by a factor of 2 or 3, but not off by a factor of 1,000,000. For a theory from 1900 that ignores quantum mechanics, that's remarkably close. It's a great first draft of the story. However, as good as the classical model is for a first guess, it is ultimately incomplete. When scientists started making more precise measurements, especially at very low temperatures, they found places where the model breaks down completely. One of the first big failures was with heat capacity. That's a measure of how much energy you need to add to a material to raise its temperature. According to classical physics, the sea of free electrons should absorb a lot of heat energy. But experiments showed that electrons contribute very, very little to the heat capacity of a metal. The reason for this failure is quantum mechanics. The classical model was wrong to assume electrons could have any amount of energy. In reality, quantum rules dictate that electrons in a metal must occupy specific energy levels, like people sitting on rungs of a ladder. Furthermore, the Pauli exclusion principle says that no two electrons can be in the same state. This forces electrons to fill up the energy ladder from the bottom. To absorb heat, an electron has to jump to a higher empty rung. But for most electrons, all the nearby rungs are already full. Only the few electrons at the very top of the energy ladder have empty rungs to jump to. The model also fails to explain why some materials are insulators or semiconductors. According to the free electron theory, any material with electrons should conduct electricity to some degree. It can't explain why carbon in the form of diamond is a fantastic insulator, while carbon in the form of graphite is a decent conductor. The answer, once again, comes from quantum mechanics and is called band structure. The allowed energy levels for electrons can be grouped into bands, with band gaps of forbidden energy between them. If a material has its electrons completely filling a band, with a large gap to the next empty band, those electrons are stuck and cannot move to conduct electricity. Finally, the simple model ignores all interactions between electrons and makes Matheissen's rule seem more perfect than it is. In reality, the different ways an electron can scatter are not always independent. The presence of impurities can change the way the lattice vibrations scatter electrons. It's like saying the permanent red lights on your route can somehow change the behavior of the rush hour traffic jams. This violation of Matheissen's rule means the simple addition of resistances is just an approximation. So, where does this leave us? The classical free electron model is like a cartoon sketch of a person. It captures the basic features: a head, a body, 2 arms, 2 legs. You can immediately tell it's a person. It's useful for conveying a simple idea quickly. It correctly tells us that metals conduct because they have a sea of mobile electrons, and that resistance comes from these electrons bumping into things. Matheissen's rule gives us a handy, if sometimes imperfect, tool for adding up the sources of these bumps. This picture works well enough for many everyday purposes. However, the sketch is not a photograph. It misses all the fine details and textures that make a person unique. The classical model fails when we look too closely. It cannot explain the low heat capacity of electrons. It cannot explain the existence of insulators and semiconductors. It cannot explain the strange behaviors of materials at extremely low temperatures. It misses the weird and wonderful rules of quantum mechanics. To get the full picture, we need band structure. And we need quantum statistics. The journey from the simple classical model to the quantum description shows how science works. We start with a simple idea that explains obvious observations. Then we test it with better experiments. When the model breaks, we don't throw it away entirely. We learn and build a new, more powerful model that adds the missing pieces. The classical model isn't wrong. It's incomplete. It remains an essential first step for students. Takeaway. Think of electricity as a river of electrons flowing through a forest of vibrating atoms. That metaphor gives intuition for resistance, for temperature, and for current. It's a story that gets the main characters and basic plot right. But remember, it's simplified. At the atomic scale, quantum mechanics rules, adding layers of depth and complexity. Science is a continuous journey toward a more complete picture.